Okay, reading quiz 14 is about Euler's method. We've used tangent line techniques before to help approximate solutions to things we don't necessarily know the solutions for. And now we get a little more fancy with that. We're going to use a technique where we're going to basically adjust our tangent line on small increments. Euler's method is not the most accurate method that you could have. There are many others that you may study in your differential equations classes later on. But it does give you a nice idea of another technique we can use to approximate solutions, especially to differential equations we don't have solutions for. So let's take a look. What is Euler's method? Just like I mentioned, in order to help us approximate solutions to differential equations, we use this technique called Euler's method. In reality, this method is just a fancy version of a tangent line approximation. The idea is that we're going to use one tangent line approximation to help us get a more accurate guess for a solution. It's almost like we're using tangent line segments. And once we get to the end of a segment, we're going to create a new tangent line based on the slope of that segment. And this will allow us to come up with an even more accurate tangent line approximation. And this picture was borrowed from Wikimedia. Application of the formula. So we're going to go through a progression of guesses that will help us figure out what our approximation is. We will say that guess 1 for y can be found by using a tangent line around guess 0. So y sub 1 is equal to y sub 0 plus the slope at that point, x sub 0, y sub 0, times whatever the x sub 1 minus x sub 0 is, which we're going to call delta x. That's a little delta symbol there. That's the change in our x. Guess 2 for y can be found by using a tangent line around guess 1. So in this case, you notice the changes here. y2 is equal to y1 plus the slope at the point x sub 1, y sub 1 times our change in x, which normally stays fixed. So you can reason that guess n plus 1 can be found by using a tangent line around guess n. As you can see here, n plus y sub n plus 1, or new guess, is equal to y sub n plus the derivative x sub n, y sub n, times whatever our delta x is, our change in x. So our example, suppose dy dx is equal to y minus x, and that y of 0 is equal to 2. Use Euler's method with step size 0.2 to approximate y of 1. And later on we'll ask the question, will this be an overestimate or underestimate of the actual value? Now, not all of your Euler's method problems will be this complicated. When you see it on the AP exam, you won't generally have a calculator. And so they'll give you pretty simple numbers to work with. I just wanted to show you an example of kind of a more complicated one first so that we can work down. So typically when you're doing Euler's method, you want to set up a chart. And what I've done with my chart is I've got my number of guess that I'm on first, our n, our x sub n, which starts out at 0, our y sub n, which starts at 2, a column for our dy dx, and then a way to figure out our next guess. So notice on our first row we've got 0, the point 0, comma 2. We use our dy dx is equal to y minus x to figure out our slope, which is 2. And so our next guess will be our y sub 0, which is 2, plus 2 times, our derivative times, our change in x. And our step size is our delta x, our change in x, which in this case is 0.2. So our new guess is 2 plus 2 times 0.2, which is 2.4. I've put that in red because then that becomes our new y sub n, our y sub 1 in our case here. Since we're going up by 0.2 each time, our new x sub n is 0.2. I just mentioned that our new guess is 2.4. We use our formula for our derivative, and we get 2.2 as our derivative. So we take our y sub 1, which is 2.4. We add that to 2.2, our derivative, times our step size, 0.2, and we get our new guess in blue, 2.84. Our x goes up by another 0.2. Our new guess goes in blue under y sub 2. We go through the same process. We get a new derivative, 2.44. We calculate our new guess, which is 3.328. That's in purple, and it goes in the next row. And we keep on going until we get our x value equal to 1. All right, kind of a rinse-repeat sort of thing. So we end up with, at 1.0, our guess would be 4.48832. Be careful you don't go too far in your chart. Once you get to x is equal to 1 in this case, then whatever y corresponds to that when you fill in your chart is going to be your answer. Okay, notice our delta x is 0.2, as we said before, and the chart gives us what we want. Y of 1 is equal to 4.8832. Like I said, typically you don't have a calculator when doing these, and so the numbers are a little bit simpler. You might have to do something along the lines of the 2.84 up here, and generally 2 or 3 step sizes. So the second part to that question, suppose dy dx is equal to y minus x, and that y of 0 is equal to 2. Will this be an overestimate or underestimate of the actual value? The cool thing about Euler's method, as you've noticed, is it's just an application over and over again of tangent lines. So just as we know with tangent lines, if our function is concave up, our tangent line under approximates. If our function is concave down, our tangent line over approximates. So taking the derivative of this and remembering the chain rule, we notice that the second derivative is equal to dy dx minus 1. Okay, and looking at the chart, we see that dy dx is always bigger than 1. Okay, so dy dx minus 1 is going to be positive for all values in our interval. Since our function is concave up, our estimate is going to be an underestimate. Okay, so again, our determination of that is very similar to what we do with tangent lines. Example 2, another chart. Going backwards this time, suppose dy dx is equal to 2y minus x, and y is equal to 3 when x is 2. Use Euler's method with 5 equal steps to approximate y when x is equal to 1.5. And again, is our answer an over or under estimate. All right, we set up our chart. We know our position initially is 2, 3. We know our derivative is 2y minus x. When we plug in y and x, we get our derivative equal to 4. And our step size, or delta x in this case, is negative 0.1. We're going backwards 5 times total for 0.5 units. So our new guess will be 3 plus 4 times negative 0.1, which is 2.6. And that goes in the next row of the chart under our y sub 1. Going backwards with our x to 1.9, we're going backwards negative 0.1. We have 1.9 as our x and 2.6 as our y. Calculate our derivative, we get 3.3. We go through to our formula, our tangent line formula, and get our next guess is 2.27. I won't bore you by going through all the parts of this chart. You just continue on. And again, when you get to x is equal to 1.5 in your chart, your guess is 1.57344. As for the underestimate, overestimate question, we notice that the second derivative by the chain rule is 2 dy dx, since we are taking the derivative with respect to x, minus 1. A quick glance at the values in the table again shows that 2 times dy dx is much bigger than 1. So our function is concave up, and we have an under approximation, again, based on our tangent lines. Example 3, this is from an actual BC exam. Consider the differential equation dy dx is equal to 6x squared minus x squared y. Let f of x be a particular solution to this differential equation with the initial condition f of negative 1 is equal to 2. The first part of this question asked you to use Euler's method with 2 steps of equal size, so a little bit simpler on the AP exam. Starting at x is equal to negative 1 to approximate f of 0, show the work leads to your answer. Well, 2 steps of equal size will be of size 0.5. So we can determine f of negative 0.5 is approximately 2 times 4 times 0.5. And where does the 4 come in? We plugged in x equals negative 1 and y is equal to 2 into our dy dx. All right, and in doing so, we get 6 minus 1 times 2, which is 4. That's our slope, and our step size, of course, is 0.5. Our initial condition is 2. We continue to do that. We get f of 0 is approximately 4 times 0.5 times 0.5. Again, the 0.5 comes from plugging in our negative 0.5 for x, and our y is equal to 4. Notice the correct use of the approximation sign in this case, because in fact we are approximating. They do take off on the AP exam if you don't include that sign. Part B, find the actual value of f of 0. This is a separable differential equation. If we factor out an x squared, we get an x squared times 6 minus y on the right side, which we can then divide onto the left side. We get 1 over 6 minus y dy, and x squared dx, and we're going to integrate both sides. We get a negative natural log of 6 minus y. My students had some problems with this when we took the exam. Don't forget about that negative inside of the the 6 minus y part. We need to put a negative outside by the chain rule. We get 6 minus y is equal to k times e to the negative 1/3 x cubed. And I should have put on there that k is equal to plus or minus e to the c. When we try to find out what k is, we get k is equal to 4. And then we can solve for y. Y is equal to 6 minus 4 e to the negative 1/3 x cubed plus 1. Plug in x is equal to 0, we get y is equal to 3.134. Notice our guess was 4.25. And our guess is a gross overestimate. When you actually go through and calculate the second derivative at negative 1, 2, you get it to be negative 12. And since the function is concave down, our approximation will overestimate. And negative 12 is a pretty big second derivative.